Hey guys, here is the last of your notes on section 4.3, day 3. The last thing we have to cover is one more theorem, and luckily it's a pretty easy theorem that we have left to cover, and it's kind of common sense. So it is the intermediate value theorem, but before we get to it, let's think about something. Suppose f of x is a polynomial function. Therefore, the graph of f is a smooth continuous curve, right? Because polynomial functions create smooth continuous curves. They have no breaks, they have no holes, no jumps, no points of discontinuity. They are just a smooth continuous graph, okay? Well, suppose f of 3 equaled -4 and f of 7 equaled 10. Then what must there have been in between x equals 3 and x equals 7? So think about it. If you plug 3 into this polynomial function and a negative number comes out, right? But then when you plug 7 in a little bit more down the x-axis, a positive number comes out. Well, what is that graph going to have to do to connect these two dots in a smooth continuous fashion? It's going to have to cross over the x-axis. So basically they're telling you that if the y value changes signs in between two x values, then you know there is at least one x-intercept in between those two x values. So it's basically giving us an interval of x to work on where you know there must be at least one x-intercept, because that's what we're trying to do with these higher degree polynomials, is narrow down what are their x-intercepts, what are their zeros, right? So if the y value is going to change signs, then you know in between those two x values, there must have been at least one x-intercept. Right? There could have been multiple. Maybe it crossed over the x-axis a few times, but we know at least one time it had to. At least one x-intercept must be there. Okay, so that's what the intermediate value theorem is saying. If you can prove that the y value has changed signs on an interval of x, then you know there must be at least one x-intercept in between those x values. Okay, so here's the fancy schmancy definition. Let f denote a continuous function if a is less than b, so a comes before b on the x-axis, and if f of a, right, the number that comes out when you plug a in, if f of a and f of b are of opposite sign, so if the y value at f of a is different than the y value at f of b, then you know they have changed signs. Then f has at least one zero, at least one x-intercept between a and b, right? So if f of a creates a negative number and f of b creates a positive number, then you know the graph in some smooth continuous fashion is going to cross over the x-axis at least once, somewhere in between a and b. Now, all this one is saying is, let's say f of a created a positive number and f of b created a negative number to come out, right? The y value has changed signs from positive to negative. Then this is just showing you that there could be maybe 1, 2, 3 x-intercepts in between a and b. So it doesn't just have to have one. By y changing signs, it's just proving that there has to be at least one x-intercept in between a and b. And now we can kind of hone in on that interval of x to determine where some of our zeros are going to be. Okay? All right, so the intermediate value theorem, together with the table feature of a graphing utility, provides a basis for finding zeros. So guys, when you're using your graphing calculator to basically ask it to calculate the zeros, this is the process it's going to go through to kind of narrow down where the x-intercepts are. It's going to look for that y value to change signs, and in between what x values it happened at. All right, so let's try it. So I've written down a bunch of steps because it's a graphing calculator problem. That way you guys would have it to use in the future if you needed to see it. All right, so here we go. Example 1 says, using the intermediate value theorem and a graphing utility to locate zeros. So the problem says, find the positive zero of f of x equals x to the 5th minus x cubed minus 1, correct to 2 decimal places. So we're finding one of the positive zeros out of 5 possible zeros, right? Degree 5. We're finding the positive one, correct to 2 decimal places. So again, if you look at this, to set x to the 5th minus x cubed minus 1 equal to 0 and calculate those zeros by hand, that's really difficult because this doesn't factor. So how are you going to start breaking that down? Other than going to your P's and Q's and coming up with a list of potential real zeros, rational zeros, we have to go to the graphing calculator. All right, so you're going to type the equation into y equals. I already did that. My my camera on here. All right. So go to y equals, I already typed the equation in, x to the fifth minus x cubed minus 1. All right. I already have another one stored for the next example, but I'm just good with this one right now. And it's the only one I have turned on, right? I've turned this one off because equal sign is not lit. All right. So now if you just go right to his graph, right, you can take a peek at where the x-intercepts are. So if you look at his graph, right? Look at what it's doing. It definitely crosses over the x-axis between 1 and 2. Now, the intermediate value theorem would have you just prove that when you plugged f of 1 in, a negative number came out. When you plugged 2 in, a positive number came out. There was that change in y's sign. That's how you can prove there's definitely x-intercept in between 1 and 2. But we're going to let the graphing calculator figure that out, right? So we know that somewhere in between 1 and 2, there's going to be a positive 0. So we have to find it, correct to 2 decimal places. All right, so what we're going to do is we're going to use the table feature. So we're going to look at the graph to see its x-intercepts. We just did that, right? Now press second graph to go to the table. So second graph, right? If you look at the table, I should probably start how your table would normally look. Normally your table is set up like this. It starts at 0 and the delta table, the change in the increment is 1. So second table. So what you're basically doing is you see how when x was 1, there was a negative y value, and when x is 2, there's a positive y value. So that right there is the intermediate value theorem proving that since the y value changed sign from negative to positive in between 1 and 2, then there's definitely an x-intercept in between 1 and 2. Okay, so the table kind of shows us what that's happening. Now you have to scroll through it to the table until you see y change signs. Well, we didn't really have to scroll because it happened rather quickly that the y value changed signs. But in some problems, maybe you have to scroll and scroll and scroll until you see the y value change from negative to positive or positive to negative, okay? But luckily ours was rather close to where x was 0. All right, so we scroll through, we'd see where the y value changes signs, all right? We saw that was between 1 and 2, right? Okay, so that's where we're going to concentrate. We know there's an x-intercept between 1 and 2. To narrow down the answer, right, correct to 2 decimal places, we will have to divide the interval between 1 and 2 into 10 subintervals. So you're basically taking the interval between 1 and 2 and you're chopping it into tenths. You're chopping it into 10 subintervals. And now you're going to hone in on those little subintervals and find out where y changed sign again. All right, so to do that, you're going to go to second window because you got to get to your table set. So second window gets you to the table set feature, all right? Well, we know that the y change signs in between 1 and 2. So we want our table to start at 1, the beginning of that increment, 1, and then we want the change in the change in the table, the increment, we want it to be in 10 subintervals, right? So I'm going to go to a tenth, 0.1. So I'm going to let my delta table be 0.1. All right, hit enter. Now go back to the table. All right, so second graph gets you back to the table, right? I'm going to start the table at 1, and I'm going to let the increment be 0.1 to kind of cut it into tenths. All right, go back to the table, second graph. And now you're going to scroll through the list and find where y changes signs again, right? So now scroll through, see how y is negative, negative, negative. Oh, now he's positive. So that means that it was when x was 1.2, y was negative. When x is 1.3, y is positive. So now we know somewhere in between 1.2 and 1.3 is where there's an x-intercept. We're narrowing it down, right? So now we know somewhere in between 1.2 and 1.3 there's an x-intercept. So we've narrowed it between 1 and 2 to now somewhere in between 1.2 and 1.3. Well, they asked us to be correct to 2 decimal places. So now we're going to chop the interval between 1.2 and 1.3 into 10 more subintervals. We're going to narrow it down even more. All right, so now go back to your second window. Let's go back to that table set, second window. Let's change the table. Let's start at 1.2 now. All right, and let's go to 2 decimal places. Let's chop it into 10 more subintervals. So now let the delta table, the change in table, the increment be 0.01. That's our second decimal place. Hit enter, and now let's go back to the table again, right? Now we're letting it start at 1.2, and we're letting our increment be 0.01. All right, now we're going to go back to the table. So second graph, Go back to that table, and now let's scroll, and now let's find where it changes signs again. So it's negative, it's negative, it's negative, it's negative. Oh, now it's positive. So you see how when x was 1.23, it was negative. When x is 1.24, it's positive. So that means there's an x-intercept in between 1.23 and 1.24. Now, since they only asked us to find it correct to 2 decimal places, I can stop right there. So we know it's somewhere in between 1.23 and 1.24. So reading the graph from left to right, we keep the 1.23 as our answer. So we're going to say correct to 2 decimal places, there is an x-intercept at 1.23. Okay, and that's exactly how your graphing calculator works. It keeps chopping that interval into subintervals until it can narrow it down to a more exact answer. Okay, now since it asked correct to 2 decimal places, you could have started right away at your table start at 1 and then going right to the 0.01. It's just, I wanted you guys to see that we were chopping it into more and more subintervals, but because they asked for 2 correct decimal places, in the future, if you want to start at 1, right when you know where it's in between, and go right to the 0.01, it's just going to take you probably a little bit more scrolling to find where y changes from negative to positive or positive to negative, but it'll go right to that 1.23, 1.24 and save you the step. I just wanted to kind of take it in steps to see that that's the process the graphing calculator is doing. It just keeps chopping that interval into more subintervals until it can get to a more exact x-intercept, okay? So again, in the future, if they ask for 2 correct decimal places, I would find out in between what 2 numbers it has an x-intercept, and I would start it at 1, and I would go right to the 0.01 as my delta table, and then you can get your 2 decimal places in one step, okay? But that's how you can do it, okay? All right, let's try it again. So it says, use the intermediate value theorem to show the function has a 0 in the given interval. Approximate the 0 correct to 2 decimal places. Okay, let me just move this up. All right. So if the intermediate value theorem says that this polynomial will have an x-intercept in between 0 and 1, they've given us an interval to concentrate on in between 0 and 1, we have to prove that the y-coordinate changes signs when you plug 0 and 1 in. So using the intermediate value theorem, if I found f of 0, right, if I plugged 0 in for all of these x's, well, it would be 0, 0, 0, negative 1. Negative 1 would come out. So when 0 gets plugged in, a negative number comes out. When 1 goes in, right? 1 to the 4th is 1, 1 squared is 1, it's 1. So all the numbers will stay the same. 8 times 1, negative 2 times 1, 5 times 1. So it'll be 8 minus 2 is 6, 6 plus 5 is 11, 11 minus 1 is 10. So when 1 goes in, a 10 comes out. So you see how when you plug 0 in, a negative number comes out, but when you plug 1 in, a positive number comes out? That means that the graph has to cross over the x-axis somewhere in between 0 and 1. There's got to be an x-intercept somewhere between 0 and 1 since the y-coordinate changed signs. So guys, that's basically the intermediate value theorem part. It's proving that y changed signs, so there's got to be an x-intercept in between 0 and 1. Now we're going to let the graphing calculator do the heavy lifting and approximate it correct to 2 decimal places, okay? So we're going to go to, first you'd have to type this equation in. So I would go to y equals, I'm going to turn this one off. I'm going to turn this one on. I already plugged it in. So type that equation in, right? Now you're going to go to second table set. And again, if you want to look at the graph really quick, go ahead. Look at the graph. All right. It definitely crosses the x-axis in between 0 and 1. It looks like it's pretty close to 0, more so than 1. But there's definitely an x-intercept in there. There's another one over here, but they asked us to concentrate on the one that was in the interval 0 to 1. So we're going to find that one right here. So let's go to second window. Let's go to table set, right? We know it's asking us in between 0 and 1. So let's start our table at 0. And then it asked us to be correct to 2 decimal places. So let's go right to the 0.01 as our delta table, as our change in the table, as our increment, right? And we'll go right to our table now, second table, and we'll start scrolling through to find out where the y-coordinate change signs. All right, so moving from 0 to 1, right? Look at all the y values. They're all negative. So we're going to keep scrolling until we see the y-coordinate change to a positive. Negative, 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 negative. Oh, there it is. All right. So see how y was negative, 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 and then right there it was negative, and now it's positive. So when x was 0.21, it had a negative y coordinate. When x is 0.22, it has a positive y coordinate. So we know there's an x-intercept right there. So since they've only asked us to approximate it correct to 2 decimal places, then we're going to keep the number right before it changed. So it was negative, 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 and then it changed. So we're going to keep this one right here, x equals 0.21, as our approximate x-intercept, our approximate 0 in between 0 and 1. All right. So again, that's how I think my math lab wants you to do it. They want you to keep the last one before it changed signs. So keep this one as your answer, the 0.21 instead of the 0.22. I think last year kids were getting marked wrong for putting 0.22. So they want you to keep the one right before it changes. Okay. All right. And that's how we can use the graphing calculator and the intermediate value theorem to approximate zeros. Okay. All right. Now, just to give you a hint. So when you are given these increments and you're, putting your delta table to 0.01, when it's a positive increment, like on an increment of x from, or an interval of x from 2 to 3, right? You start your table at 2, you put your table at 0.01, and you scroll down until it changes, right? So when you're doing it this way on a positive interval, let's say y was negative, 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 and then positive. Like I just said, it tells you to keep the last one before it changed sign as your correct answer. That's what my math lab was doing last year. Now, if it's a negative interval of x, right, -3 to -2, well, what we were finding last year on my math lab is start your table at -2, all right, and scroll up on your list. So start it at -2, and then instead of scrolling down, scroll up until you see the y value change sign. So start it at -2, and let's say it was positive, 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 and then it switched to a negative. All right, it looked like my math lab, again, was keeping the last one before it changed to the opposite sign. So it would keep this one as the correct answer, okay? Just so that you guys don't get that one wrong, because I think a lot of students were scrolling, starting at -3 and scrolling down and keeping the last one, but my math lab was marking them wrong. So I think on these negative intervals, they want you to scroll back or up and find the one right before it changed, okay? All right, and that's it. All right, so if you have any questions on the intermediate value theorem, please feel free to reach out to me and let me know. All right, good luck on your homework, and I'll see you guys later.